Sending requests to threads via channels. Okay, that took a turn. Now we'll tackle the problem that the closures given to thread spawn do absolutely nothing. Currently, we get the closure we want to execute in the execute method, but we need to give thread spawn a closure to run when we create each worker during the creation of the thread pool. That is a predicament. So they're stating that when we initialize a worker, in order to run the thread spawn, that method, we have to give it a closure at that time, and that's why we give it an empty closure. But it's not until later when we do the thread pool execute method, run that one, that we actually have the closure we really want to run in our thread pool. So that's something that needs to be fixed now. We want the worker structs that we just created to fetch code to run from a queue held in the thread pool, and we'll send that code to its thread to run. Oh, they're going to use channels as a queue, which makes sense. In chapter 16, you learned about channels, a simple way to communicate between two threads that would be perfect for this use case. We'll use a channel to function as a queue of jobs, and execute will send a job from the thread pool to the worker instances, which will send the job to its thread. Here's the plan. 1. The thread pool will create a channel and hold on to the sending side of the channel. 2. Each worker will hold on to the receiving end of the channel. 3. We'll create a new job struct that will hold the closure we want to send down the channel. 4. The execute method will send the job it wants to execute down the sending side of the channel. 5. In its thread, the worker will loop over its receiving side of the channel and execute the closure of any job it receives. Alright, so just to summarize, it sounds like the thread is going to create the channel. It's going to hold on to the sending side of it. And then each worker is going to have access to the receiving side of it. And execute is going to be passing the closure from the sending side to the receiving side, and a worker is going to pick it up. And whatever worker picks it up is going to complete that job. Let's start by creating a channel in thread pool new and holding the sending side in the thread pool instance, as shown in listing 20.16. The job struct doesn't hold anything for now, but will be the type of item we're sending down the channel. And I forgot all about the job struct. The job struct will hold the closure. Okay, it's a wrapper. Got it. Wrapper for closures. So we implement what we need for a channel, which I forgot what the multiple P single consumer. Oh, multiple producer single consumer? I think that was it. Yeah, that's for channel. Cool. So actually, let's read this code before we copy it over. So we import channels. We have the sending side, which is the channel, sender, job. Job is just an empty struct for now. Our new for thread pool now creates a channel, has the sender and receiver, and the sender is being added to the thread pool. So that's the only real differences at those 3 to 4 lines. So let's do them one by one. That's not it. This is it. Alright, come back to libs. Alright, let's copy this over. Almost went all the way to the top again. Paste. And now add senders to thread pool. Add the line where we create the channels. And that's after the assert. And then we add sender to the thread pool. Cool. Oh, we forgot to add job. And that's everything, so the check should pass. It compiled. In thread pool new, we create a new channel and have the pool hold the sending end. This will successfully compile, still with warnings, and we saw that. Let's try passing a receiving end of the channel into each worker as the thread pool creates the channel. We know we want to use the receiving end in the thread that the workers spawn, so we'll reference the receiver parameter in the closure. The code in listing 20.17 won't compile yet. Okay, so here's the channel, here's the receiver from the channel, and when we create the workers, we're passing ID and the receiver, and that means our workers have to change. So the new for the worker now takes in a receiver job, and I'm not sure if that was there before, but it should have been there. Our workers were always returning workers, so that should be fine. So let thread spawn, and you pass in the receiver and ID and thread. So it's not too different. All right, let's. Where did it go? Where did it go? Here we go. Let's write that. Here is new. I keep scrolling past it for some reason. And this is the wrong one because that didn't have channels in it. This has channels in it, but it's not passing the channel. And here's the correct one. So this is what we really want. This new line. And then we have to change our implementation of workers. Which worker is currently returning a worker, but just change this new. Now, receiver's there. Oh, it looks like this code is not going to compile. They have an error right there. So that makes sense. Let's see what they have to say. We made some small and straightforward changes. We passed the receiving end of the channel into worker new, and then we use it inside the closure. When we try to check this code, we get this error. And just to verify, cargo check, we get an error, and this value has been moved here in previous iteration of the loop. And here, this is when the move occurred. Okay, we have some borrowing errors. Is that what they have here? Yeah, it was already moved. The code is trying to pass receiver to multiple worker instances. This won't work. As you recall from chapter 16, the channel implementation that Rust provides is multiple producer, single consumer. This means we just can't clone the consuming end of the channel to fix this code. Even if we could, that is not the technique we would want to use. Instead, we want to distribute the jobs across threads by sharing the single receiver among all the workers. This is very true. We know that the channels are multiple producer, single consumer. Consumer would be the receiving end, so there should only be one of those, i.e. single consumer. So we shouldn't be copying it, or cloning it, which is what they mentioned here. Instead, we want to distribute the load that the sending end is, that the receivers are going to have, like distribute it among the different workers. I'm not exactly sure that we're going to do that, but let's see. Additionally, taking a job off the queue involves mutating the receiver, so the threads need a safe way to share and modify receiver. Otherwise, we might get race conditions, as covered in Chapter 16. Recall the thread-safe smart pointers discussed in Chapter 16. To share ownership across multiple threads and allow the threads to mutate the value, we need to use arc mutex t, the arc type. Will let multiple workers own the receiver, and mutex will ensure that only one worker gets a job from the receiver at a time. Listing 20-18 shows the changes we need to make. Okay, that makes a lot of sense. Arc, we know, allows you to use things in a thread-safe manner, and Mutex has the API where only one person can get access to it at a time. And given that we have only one receiver, this means that we're going to give everybody access to the same receiver, but the unlock and lock of the Mutex is going to make sure that only one of the workers pulls work from it at a time. That seems kind of like a hack, but that makes a lot of sense. That makes a lot of sense. All right, so let's see how they implemented it. They import arc and mutex. Makes sense. They wrap the receiver in an arc and a mutex. So wrapped in a mutex first, then that's wrapped in an arc. They do arc.clone a pointer to receiver, which is all you really need to do. And then they have to change the interface for the new worker. That makes sense. Move that over. I'm not seeing my line. Here we go. Start with the imports. Arc and mutex. Wrap the receiver. That is right. Move that out of the way. You can get the full side of this window. So that's above workers right here. Wrapping the receiver. And then worker new ID. We're not passing the direct receiver now. We're passing this. That looks correct. And in terms of the worker, we need to change the signature. So you're no longer going to be a receiver. You're going to be this thing. Which is arc, mutex, channel, receiver, job. Yeah, that looks like it corresponds. And should that get rid of our errors? It compiled. It compiled. There are warnings, but it compiled. All right, here we are. The thread pool new, we put the receiving end of the channel in an arc and a mutex. For each new worker, we clone the arc to bump the reference count so the workers can share ownership of the receiving end. With these changes, the code compiles. We're getting there. Implementing the execute method. Let's finally implement the execute method on thread pool. We'll also change job from a struct to a type alias for a trait object that holds the type of closure that execute receives. As discussed in the Creating Type Synonyms with Type Alias section of Chapter 19, type aliases allow us to make long types shorter. Look at listing 20-19. So our job is going to be a box. It's going to be dynamic function once, send static. So this is the signature for the closure, which we already know from looking at thread spawn. And we're dynamic. I think that's just part of the syntax that we use now for when we put things in the box. And boxes means we're going to have a pointer to it, because a closure itself, I don't believe is sized. But a box gives you a pointer, which is sized, and the compiler likes sized things. And then execute. It's going to create a job, box, new, and the closure that's passed in. And then self.sender, which is the sender that's on thread pool, send, job, and unwrap. I forgot what the unwrap does. I'm pretty sure it'll explode if there's an error, but I'm not too clear on where it would explode, whether it explode within the worker or the thread pool struct, the parent struct. Anyway, let's start writing this. Smooth that over. Where did you go? Where did you go? Here it is. Okay. So job got changed. Type aliasing. Type job, and that's what it means. And now we have execute, which was pretty empty before. And that looks about right. Cool. Here we go. After creating a new job instance using the closure we get in execute, we send the job down the sending end of the channel. We're calling unwrap on send for the case that sending fails. This might happen if, for example, we stop all of our threads from executing, meaning the receiving end has stopped receiving new messages. At that moment, we can't stop our threads from executing. Our threads continue executing as long as the pool exists. The reason that we use unwrap is that we know the failure case won't happen, but the compiler doesn't know that. So they explain the unwrap portion. We use it just in case the sending of our job fails, and that could happen when the receiving end has already been closed and is no longer receiving jobs. But we know that the code we're writing doesn't fall into that category. That's never going to happen. But the compiler doesn't know that, so we need the unwrap there just in case. So the compiler will be satisfied. Which, thank you, compiler. Keep us honest. But we're not quite done yet. In the worker, our closure being passed to thread spawn still only references the receiving end of the channel. Instead, we need the closure to loop forever, asking the receiving end of the channel for a job and running the job when it gets one. Let's make the change shown in listing -20-20 to worker new. All right, let's see what we have here. The signature still stays the same from the last time we wrote it. We have thread spawn, move. So moving things into the closure. We have an infinite loop. So within the closure, we have an infinite loop where we let job equal receiver dot lock unwrap receive unwrap, which is just trying to pull off a job from the queue, and then it's going to print worker blah blah blah, whatever ID, got the job and just executing it, and then it's going to run the job, which is the closure, and it's just calling it here. So that makes sense in theory, but according to this icon, it's not going to compile. And yeah, let's copy this over. I'm kind of curious as to why it's not going to compile. It compiled. What's the point of this icon if it's gonna lie to me? Okay. It did say not compile, right? This code does not compile. Okay. Here, we first call lock on the receiver to acquire the mutex. Then we call unwrap to panic on any errors. Acquiring a lock might fail if the mutex is in a poison state, which can happen if some other thread panicked while holding the lock rather than releasing the lock. In this situation, calling unwrap to have this thread panic is the correct action to take. Feel free to change this unwrap to an expect with an error message that is meaningful to you. So yeah, what they're saying here is that the lock is to acquire the mutex, and when we unwrap the mutex, that could be in an error state or a poison state. So unwrapping is the correct thing here, because if there's an error, we just want to panic. That's the only thing we really can do. But if you wanted to have some sort of a messaging that is more specific to what the error actually is, you can swap that out with an expect and then write your error message. If we get the lock on the mutex, we call receive to receive a job from the channel. A final unwrap moves past any errors here as well, which might occur if the thread holding the sending side of the channel has shut down, similar to how the send method returned error if the receiving side shuts down. Okay, so given that we've gotten past the mutex and the mutex is fine, we then call receive to try to get a job from the channel. And then we have to call unwrap there because there could be errors in the channel. Like one end, you could be trying to call receive on a channel that's closed from the sending end. And then boom, it should blow up. So calling unwrap here is fine, and that makes sense. The call to receive blocks. So if there are no jobs yet, the current thread will wait until a job becomes available. The mutex ensures that only one worker thread at a time is trying to request a job. All right. So here's the magic of the situation. The mutex, only one of the workers can acquire the lock at a time. So each worker has an infinite loop, right? And they're each trying to acquire the lock. Only one of them is going to get it. So let's say there are 5 workers. One of them acquires the lock. Everybody else is waiting for the lock to open. So the next job that comes is going to go to this worker. He's going to pull it off the queue and then try to execute it. And then he's going to release the lock. And then somebody else is going to acquire the lock, one of these 4, and then they're going to wait for the next job. So once this person's finished, he now goes back into the queue, move my thumb all the way to the end of my pinky, and he's waiting for the lock to open because he has the infinite loop and he's trying to read the mutex, but somebody else already has access to it, and that's either this person or this person or this person or this person, because my thumb is, you get it. With the implementation of this trick, our thread pool is in a working state. Give it a cargo run and make some requests. Okay, so we still have, I guess, warnings, but we could try it out. Cargo run. It is running. Sleep. Oops. Create another one. Localhost. Hello. So that's 3 different ones, and then we can run this one again. We can run this one again. Run this one again. That one just finished. Run it again. Go to our editor, and now we can see our jobs. So we see the worker 1, worker 2, worker 0, worker 3, 2, 0, 1, 3. Okay, this is working as expected. And they have the same code here that's running. It's just their output. And we still have the warnings. So warnings exist. Cool. Success. We now have a thread pool that executes connections asynchronously. There are never more than 4 threads created, so our system won't get overloaded if the server receives a lot of requests. If we make a request to sleep, the server will be able to serve other requests by having other threads run them. And more or less, that was the goal. We now have the ability to run multiple requests at a time, or to handle multiple requests at a time, and at least for the first 4 requests, nobody's going to wait for one of the previous requests to finish in order to be processed. Note, if you open Sleep in multiple browsers, windows simultaneously, they might load one at a time in 5-second intervals. Some Sleep web browsers execute multiple instances of the same request sequentially for caching reasons. This implementation is not caused by our web server. Just a warning here, some web browsers have some, I guess, weird ways or that they go about handling requests to the same endpoint in multiple tabs, and they may do it sequentially for caching reasons, which makes sense. I mean, if you have one browser open and 4 of the tabs go to the same page, why do you want to make that same request 4 times? You could just wait on the first one and then copy it over, save it to your cache. Meh. After learning about the while let loop in chapter 18, you might be wondering why we didn't write the worker thread code as shown in listing 20-21. I wasn't wondering that, but let's see why. While let, OK job, receive, lock, unwrap, receive, and receive doesn't have a unwrap on here, which is weird, but I guess that's because it's OK. Print, worker, blah, 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 job. So that seemed like a reasonable way of writing it, because unwrap would just have, I guess, an OK or an error, right? But this code compiles and runs, but doesn't result in the desired threading behavior. A slow request will still cause other requests to wait to be processed. The reason is somewhat subtle. The Mutex struct has no public unlock method because the ownership of the lock is based on the lifetime of max guard T within the lock result Mutex guard that the lock method returns. At compile time, the borrow checker can then enforce the rule that a resource guarded by a Mutex cannot be accessed unless we hold the lock. But this implementation can only result in the lock being held longer than intended if we don't think carefully about the lifetime of the Mutex guard, because the value in the while expression remains in scope for the duration of the block. The lock remains held for the duration of the call to job, meaning other workers cannot receive jobs. Oh, okay, I think I understand it. In this implementation, the lock doesn't unlock until after the job has been completed, because the job is within this scope. And because of that, that means that the second request is not going to happen until the Mutex unlocks, which implies that the second request is going to have to wait till the first one is done. And that is the reason why we didn't use implementation. So in the implementation we have here, right, we do the unlock here, but I'm guessing it immediately, like after this happens, it drops access to the lock. It's no longer, it like relinquishes it and says somebody else can use it, and then the job can run freely out without blocking the queue, without like monopolizing the Mutex lock. Okay, so that sort of makes sense. By using loop instead of acquiring the lock and a job within the block rather than outside it, the Mutex guard return from the lock method is dropped as soon as the let job statement ends, which is what I just stated, which makes sense. It doesn't really, visually can't really see it, but that does make sense that it happens that way. This ensures that the lock is held during the call to receive, but it is released before the call to job, allowing multiple requests to be serviced concurrently. And with that, this was a long section. If you enjoyed it, hit like, subscribe, Outside of that, there's one section left. Peace.